Hello everyone. This video is all about the concept of preparing source code to become compiled to an executable that performs the following task. It reads a global variable string type named text, T-E-X-T, which contains text, and the main program parses the text and performs a static analysis on it that yields a Boolean value. And it prints OK to standard out if the text passes the test, and it prints error blah on line blah to standard error if the text does not pass the test. There's no arguments and no input. And then after it prints either to standard output or standard error, a single line in each case, it exits. So you're guaranteed a single line of output, and it's going to be either to standard output or standard error, never both. And furthermore, it's deterministic because there's no input and no arguments. So if you can read this type of program and you can understand English, you know what the words OK and error mean, then you can reason about the operation. It's a Turing program. It's you can, in theory at least, convert any such program to a Turing machine that, when run from the initial state on an empty tape, let's say a single-sided tape, so a tape with cells indexed by the natural numbers. Okay. Plain vanilla Turing machine. That you can, and if you assign the error and OK output on standard output or standard error to special symbols in the Turing machine alphabet. If you do that, then what you can say is that the output of running the executable is identical to the output of running the Turing machine. And when we say the output of running the Turing machine, we mean the symbol under the read-write head when the Turing machine halts. That is the output. Actually, I may be wrong in this technically. I think the following adjustment may have to be made, which is that multiple symbols are added to the special symbols are added to the Turing machine alphabet, and the output of the Turing machine is the segment of tape cells, contents of the tape cells, the mark, the presence or absence of a mark, and which mark it is, the identity of the mark. That tuple is the output from one special symbol designating the beginning of output to another special symbol designating the end of output. Because we want to put the line number, we want to output the line number. So that's, in theory, any natural number. So we actually need furthermore, we need a way of encoding natural numbers. Well, not really, because what we can do is we can just use the digits. We can just assign the ASCII digits 0 through 9 to special symbols of the Turing machine alphabet. Oddly enough, I think it's actually easier if initially you work with a Turing machine with countably infinitely many symbols to represent the natural numbers. And then you can get away with having an output associated, just having a single, how to put this, then mapping the special output symbols in the Turing machine alphabet to the natural numbers. So you have a copy of the natural numbers, and a natural number, as far as the Turing machine is concerned, always designates a line number written to standard output. And actually what we need is multiple copies of the natural numbers, because we need a copy of the natural numbers for every type of error. So in other words, we're taking the Cartesian or direct product of the set of error messages with the set of natural numbers. And this designates one kind of outcome, which is printing the error and the line number, the error type and the line number to standard error. And then you have separately, disjoint from that set, another type of output symbol in the Turing machine alphabet, and that is OK, or success. So that's basically, so you start there, and then you figure out an encoding, and then you map that Turing machine to one with a finite alphabet, where you have different symbols for the errors and for each digit. So then an error mark on a Turing machine tape cell, followed by a number of digits, represents output to standard error. And then so when the Turing machine halts on the first tape cell in that segment of tape cells, that designates the output. You can see how much effort is required to establish this, what is I would describe as a homomorphism, or a type of homomorphism. What is preserved is the meaning of the static analysis that is performed by the source code. And furthermore, it's worth pointing out, this is a very, an object lesson in the halting problem. That there is, if you have a bad version of this, sort of a non-example that never halts, that just keeps, goes into an infinite loop, instead of printing to standard error or standard output and exiting, that's a non-example. That's not one of the... If you try to read that and then figure out, do a static analysis on that, there's no general procedure because of the halting problem.